think we're seeing folks gather around here. Let's give it just one more minute before we can officially kick it off. Great. We're at just 1 minute past 11, so why don't we go ahead and get started. Good morning, everyone, and welcome to day 4 of the Summer CPD Week, co-hosted by the Actuaries Club of Boston and the ACHS. For today, we have Jason Reed coming to talk to us about quantile regression as a new technique for risk scoring and predictive modeling. Jason is a health actuary and statistician at Optum, specializing in predictive modeling and data mining applications. He has over 10 years of experience applying advanced analytics to pricing, trend estimation, and underwriting prediction. He has a master's degree in statistics and applied mathematics from Texas A&M University and currently lives in Boston. Jason is also an active member of the Actuaries Club of Boston's planning committee, so we're really happy to have you here today, Jason. Before I turn it over to Jason, just a real quick note that like the other sessions today, we'll also have Q&As at the end for about 10 minutes or so. And again, you may choose to either just simply unmute yourself and ask any question live, or you can also choose to submit your questions via email to the addresses shown below right here, president.actuariesboston@gmail.com. or info@achsmembers.com. Cool. So without further ado, I'll turn it over to Jason now.
Great. Thank you very much. And thank you, everybody, for your time and for being, let me see if I can share my screen. Yes. Okay. So, hey, is this okay?
Yep.
Great. Okay, great. So I'd like to talk about, it's not really a new mathematical technique, statistical technique, but it's a sort of new in the sense of computationally new, in the sense that it's like a new possible thing for us to be able to investigate. As actuaries, and the idea, it's called quantile regression, and the idea is that like we can expand our sense of what's possible in terms of future claims prediction and future risk prediction by understanding not just the expected value of a distribution in terms of the different covariates that you use to predict relative claims risk or health risk, but also all the percentiles and in fact the entire distribution as a function of those things. And that has a lot of applications and is really going to expand our horizons. So if I start with an example of kind of current underwriting today, you know, what you might look at if you had two groups like Larry's Lumber and Bob's Trucking here is years experience, PMPMs in years 1 and 2. You might look at that. You might think about your overall block trend and think about different like characteristics of the groups. You might look at high cost claimants and the reinsurance risk from them, but we don't know a whole lot more other than these actual experience PMPMs. So how you're actually going to rate these groups in year 3 is it's hard to kind of have a good scientific way to do that. You might look at the average. You might say, well, these guys are trending below the average or above the average. But quantile regression is a method that kind of gives us a sort of an extra dimension to understand where claims are moving. And the idea is that it'll say, okay, here's what we've experienced. There's 370 and there's 340 PMPMs for Larry's Lumber, for example. And it'll say, well, not just what those PMPMs were, but like, were they high or were they low relative to the actual group morbidity? So in terms of like how your block looks and the morbidity distribution of your block and what that cost tends to be, how does this morbidity actually look? And so this is what I'm trying to illustrate here in these pictures. So what quantile regression tells us is the whole
Jason,
distribution. Yes?
Sorry to interrupt. We're still seeing the title slide.
Got it. Okay, so that's in Zoom here. It's showing up, but let's so that's Zoom. So how do I show the Zoom screen here? Hold on, let's try this. No. Now do you see?
We're seeing a
still just this. Okay, sorry. So that's okay. We'll share from here then. Sorry. Oh, that's interesting. But it's showing up as a, well, I guess I can sort of manually. It's a low tech way of doing it here. So now do you see this Larry's Lumber and Bob's Trucking?
Yes.
Okay, yeah. So that's funny. The other two screens have it, but the main one doesn't. So so anyway, here's the two groups that I'm talking about. There's their experience in years 1 and 2 for Larry's Lumber, and here's maybe the average over these two groups if you assume that these are trended to the current time, and then for Bob's Trucking the same. And so what I'm trying to expose is to say, okay, what if we know not just how the actual experience worked out, but how that experience sits in terms of the possible range of claim outcomes that group could have had. So here, what this confidence interval is showing me, which quantile regression is going to reveal, is that this 370 PMPM in year 1 represents the 85th percentile of claims for that group in that year. And the 340 in year 2 represents the 70th percentile of claims. So here you're kind of seeing that there's like a regression to the mean going down for Larry's Lumber, whereas for Bob's Trucking, it's the opposite. This 360 that they had actually represents relatively sort of a little bit unusually low claim experience relative to their morbidity distribution, and the same with year 2. Except that it's kind of going up, it's kind of regressing to the mean going upwards. So the power that I'm talking about is to say, okay, looking at the claims and the morbidity distribution that a group actually has, we can understand the entire distribution of possible claims outcomes, and we can make inferences about where we think that experience is going. It's like kind of like a whole new dimension of things. So we don't just know a single number, like a PMPM over time relative to the block. So instead of comparing it to the block, we can compare it internally to that group's experience. So that's what we're going to be able to compute here. And so how does that work? So so with quantile regression, it's like modeling the entire claims distribution instead of just the expected value as risk scores would do today, or looking at actual claims experience. So instead of just looking at the mean or some blend of the mean, some expected mean, or some manual rate, we're constructing this claims probability distribution in a similar way to how group risk scores are built today. So risk scores are built using regression techniques typically today. If you think about you know, any of the main risk score vendors out there, Symmetry or Mara or anything like that, they're done by forecasting the expected value of future claims as a function of things like age and gender and your risk profile. And they're usually done at a member level, right? So this here I just put one risk category, but you can imagine there are actually probably like 200 of those, right, in a typical risk scoring model. And the thing is, these coefficients are fixed, right, because they're representing the expected value. So your age will always get the impact of 1.2 for an incremental year, and your gender will always get the incremental 2.9, et cetera, et cetera. So what's different about quantile regression, what it's doing is this entire distribution. So instead of just estimating the expected value, we're estimating all the percentiles of that projected future claim distribution as a function of these same covariates that we previously only predicted the expected value as a function of. So you can see here that the impact of age is different at like the 25th, the 50th, and the 98th percentile. The impact of that's an additional year of age. The impact of your gender is different at the 25th, 50th, and 98th percentile. And the impact of your having this risk condition is also different at different parts of the distribution. And that shape, that slope can change for different ERGs. So you can see it's kind of like, instead of just having like a single impact of every condition, you can see sort of the differential impact across the entire distribution. So that's why I say it's like a whole different dimension of risk scores. So then, instead of just saying, okay, we think your expected prospective claim risk is going to be 2.3 or something like that times the average, now we can say things like, well, a 50% confidence interval for your future claims risk is 1.9 to 2.8 or something like that, right? And we can talk about different kinds of confidence intervals, and we can compare the widths of confidence intervals for different groups or different members, and we can talk about relative certainty we have of our risk projections in different parts of the block and things like that. So it really is like kind of a paradigm shift in terms of the way we think about health risk and in terms of how quantifiable it is. So what motivates the whole idea of quantile regression for me? Well, it's that, like, if you think about the way that health actuaries understand the variability of claims risk today, it's not really properly accurate because it depends on assumptions that really don't hold. So really the only way of understanding claims variability is to make some kind of assumptions about normality of those health claims from the central limit theorem and hoping that like sample averages will converge to some kind of normal distribution. But it's really not true. It doesn't work for health claims. Even if you truncate them or you take a square root or something like that, there are just too many claims in the tails of the health distribution. There's too many low severity claimants. There's a large number of low severity claimants, so there's like a large sort of hump at the low end of the distribution, and the tail is very long, and there's a lot of like these high severity like cancers or specialty drug users. And maybe perhaps in some world where there was you had millions and millions and millions of people, you could count on a central limit theorem. But in terms of the group sizes that we deal with and that we have to rate, it really isn't true. And on the other side, we have modern like data mining techniques to try to estimate the mean. There's like neural network techniques that are being peddled. There are gradient boosting type algorithms. These are interesting and good new ways to predict the expected risk of a group, given like their morbidity profile and their age and their gender, but they're still inadequate in my opinion. First of all, they only provide point estimates or most likely values, median estimates, something like that. And then the other and even more essential pitfall of these modern data mining techniques is that the way that you have to assign assign the impact of your overall risk score back to the individual conditions that drive that risk score is a little bit ad hoc. You can do like variable importance type rankings, but it's not as nice as like a regression model where it tells you, okay, for each additional year of age, you expect this much additional claim risk, or for the presence of this condition, we think it's going to add, 1.4 to your score or something like that. So there are gaps in terms of what we can get from these guys, and so that's why I think the quantile regression is really the right way forward to understand true variability of future claims risk. So kind of recapping what we've talked about so far, quantile regression is a statistical technique that allows you to estimate each percentile of that claims distribution at both the individual and group level. So the key advantage of that is that it allows you to build confidence intervals around anticipated future costs. So for example, instead of just saying, we think your risk score is a 1.8, or we think your expected cost for next year is $350 PMPM, we can say things like, no, there's a 90% chance that your claims fall between 340 and 360, or there's an 80% chance that they fall between 355 and 345 and 355 or something like that, right? So we can talk about all these different confidence intervals, and we can compare groups to each other to talk about how sure we are of our risk projection for that group in the next year. So you can stratify your groups with respect to how confident you feel you can assign risk margins. We'll talk more about that that application later. And lastly, we're able with this quantile regression to really quantify the differing impacts of a member's conditions. And we sort of alluded to that before when we looked at those equations with the ERG. But the basic idea is like the impact of diabetes, for example, at the center of the distribution is maybe represented by the risk score 1.2 or by an additional, like, say, $30. But that's not really capturing the entire risk that's represented by having diabetes, because there's a lot of tail risk, you know, relative to whether your diabetes is managed well or not, right? So out there at, like, say, the 95th percentile or the 99th percentile, there's a lot of information about what's going on for those very high-risk members that's not captured by a risk score or just looking at the actual expected costs, you know, or the average costs for those members that you have with diabetes. So you want to be able to quantify those risks in the tail. So what does it mean in terms of claim forecasting using percentiles? It's really like this picture below. So we're building a distribution for each group based on expected cost. And that distribution can be either, just like a risk score, can be either a retrospective distribution or a prospective distribution. So it can either talk about what do we think about the future costs, the whole distribution of future costs as a result of the current morbidity profile that you have, or how did your actual claim experience fall in terms of the current distribution, in terms of the costs based on the morbidity profile that you've got. So there's two different kinds of distributions that we're going to talk about. And with respect to this retrospective distribution, that's talking about, like, what's the universe of possible claim costs that you could have in your current period with respect to the morbidity that you've got. And that says something about, like, a regression to the mean type thing, right? So looking at, like, Larry's lumber down below, if this is like a concurrent or retrospective look based on the morbidity profile of Larry's lumber, and if the actual experience that you had in that year for that group was something like 355, then you might think to yourself, well, of course, there's going to be normal trend and other, you know, things for next year's price, but, like, relative to other groups, you might think, well, Larry's lumber is more likely to regress to the mean, given that there's no changes in morbidity profile, and maybe is a better candidate for discounting than if they had actually experienced, say, 323 or something in that year. So that's the advantage of being able to see that entire distribution and try to understand kind of what prospective costs look like. So here I'm trying to illustrate with a couple of pictures what really is going on, sort of one variable at a time. So the basic idea is, like, not only can you see the entire the member claim level distribution, like you think about that last picture I had, it was like at the member level, what were their actual costs and what could their future costs look like as a result of that. But you can also look based on conditions and to try to understand, like, what conditions are actually driving the risk of your groups and at which parts of the distribution. So in the most likely scenario, which are the conditions that are driving your risk? In the tail risk, which are the conditions that are driving your risk? Thinking about, like, a stop loss type of application, right, where you've got different kinds of risk driven by your conditions, where you're assuming the risk versus what you want to reinsure, right? And so there's a sort of a different look in terms of how you want to see it. And these pictures are starting to illustrate what I'm talking about. So here on the left, this is like looking at a single variable or covariate of your risk score model, but looking at different percentiles. So this might be like the gender covariate, for example, and kind of like what I have down here below. Now, gender makes a big difference at the low and middle parts of your claim distribution, in the sense that like maternity costs, or you know, the fact that females take better care of themselves in terms of like preventative care. Those things make a big difference between men and women in terms of anticipated claim costs for like reasonable parts of the claim distribution. But when you get to very high costs, very extreme ends of the distribution, say like treatments for cancer and things like that, there's not such a big difference between the two genders in terms of like the future prospective costs. So that's a really kind of important observation, because it means that when you're talking about insuring a group for their expected cost for future years, and you have two different groups, one that's all men and one that's all women, you want to, but otherwise entirely identical, you'd want to rate them quite differently in terms of their normal first dollar major medical costs. But if you're insuring that group in a self-funded type way, if you're just selling them stop-loss insurance, or if it's a level-funded premium type product where all the risk is pushed into stop-loss type risk, then you should not rate those two groups differently just based on the fact that their genders are different, right? If their conditions are the same. And if you do, then you'll expose yourself to anti-selection from carriers that do recognize the difference in kinds of risk. So that's what I'm talking about in this picture here on the left. Now, in the picture on the right, this is trying to explain kind of the guts of what's going on. So here we're looking at as if we did a quantile regression on just one variable, just one condition, like heart disease. So what quantile regression is, so what a standard risk score is like kind of like just drawing one line relative to the expected costs of that condition. And the slope of that line represents the additional expected costs from that that arise from members that have that condition. And so what's important to observe about this picture is how the slopes are changing. That's something like these, like 0.6, 1.1, well, here, that's not. So I should say, like, here, the ERG slopes, like 0.4, 4.8, and 6.7. So it's saying the differential impact of that condition is varying by the different percentiles. So when you're looking at what's going on for like high risk, at the high risk of the group, it's a different impact of that condition than what's going on at the low risk of that. So if those lines were all parallel, then quantile regression would not be needed, because it would be the same impact at all percentiles. But in truth, actually, those differences are quite dramatically different, and that's the key here. So you might ask yourself, well, that's really very interesting. So what's been going on here all this time? How come we've been using these just like regular least squares regression and the expected values, and not looking at these conditional percentiles? And the answer is computing power. So least squares regression and estimating the conditional mean as a function of percentiles can be framed in terms of a nice matrix equation in the least squares. And so it's very easy for computers to solve that problem, even for hundreds and hundreds of variables, maybe even 1,000 variables and millions of members. So it's very efficient, and it's been like thoroughly studied, and it's a really good, nice to solve problem. But the problem that you have to solve to get these quantile regression coefficients is very different. It's a linear programming problem. It's very difficult for computers to solve. Probably was not really even practical up till 5 years ago for any kind of moderately sized problem. And but now, you know, the sky's the limit, right? Everybody's got a supercomputer on their desktop, and this is totally possible. So we just want to kind of encourage this paradigm shift towards understanding way more than we did before. So so for both fully insured and self-insured groups, quantile regression can really improve our risk assessment. There are, I think, very many applications of having these new estimates that tell you about the whole distribution rather than just the expected value. Here I've just outlined a few of the estimates that I think, of the applications that I think are the most important. So for groups that are fully insured, I think in terms of setting risk charges for those groups and understanding like how to do it in a fair way in terms of the actual risk that the group brings to the block. Right now, there's no really good way to quantify that variability in the right way and to make sure that the risk charge is appropriate to what that group brings. And the quantile regression gives you that power. And on top of that, it allows you to say, well, group A versus group B may have the same, you know, expected claims, and they may have the same like expected rate for the future. But if one of them has a confidence interval for that rate that's like twice the length of the other one, then you're going to need to build in more margin into that group that has the wider confidence interval, right? Where you're less sure of what your future projections are. So you can also use quantile regression to help your underwriters provide renewal guidance in terms of which groups are good candidates for discounting versus not. I think that the groups that are good candidates for discounting are the ones that like would have a narrower distribution around the expected value, and the groups that are that have a wider distribution where we're less sure of what our estimate is supposed to be, they're not such good candidates. So your pooling strategy in terms of like how much risk is actually being taken out of the block by pooling at different levels, you can actually quantify that using quantile regression, because it'll tell you, hey, if you pool at $50,000, that's pooling at the 98th percentile. Or if you're pooling at, you know, $100,000, that's pooling at the 99th percentile. So you kind of know how much risk that there is corresponding to different strategies. I'll just mention the level funded premium product as one last very important example. Not only are you going to be able to price stop loss much better, but you'll be able to tell based on the inherent variability of the groups, kind of based on your risk tolerance, which groups you think would be good, better self-funded candidates for versus those that would probably be better off in a fully insured product, and you know, you can kind of like really understand the risks that are inherent inside each group when you understand the entire distribution of claims. So again, linear regression provides us, is what we've been using all along. It's great, right? I mean, it's great to be able to use risk scores for pricing. It tells us much more than just claims do, because it kind of takes the whole experience of your whole block kind of, you know, sort of inherently, you know, together along with the claims experience to give you a whole different estimate of risk. But it really is just a single point estimate. You can't really tell anything about variability without assuming this normal distribution, which is wrong, and without assuming constant variance, which is also wrong for groups, right? So all those nice statistical theorems that we know about linear regression just are not true in a health insurance context, and it really limits the utility of estimates that come from linear regression. So quantile regression is a partial solution to that problem in the sense that it doesn't make any distributional assumptions. It allows the claims distribution to be variable based on everybody's unique health profile, and then it allows you to build these confidence intervals as I mentioned before. So we've kind of been talking about each member's individual risk score and profile of risk scores all along, right? Where I've sort of said, okay, so as a function of, you know, your covariates, your 10th percentile is this, your 20th percentile is this, your 50th percentile is this, et cetera. So that's great in the sense that it allows you to quantify variability at a member level, but it's not like it makes that variability go away. And as we know, you know, health insurance claims are tremendously variable at a member level. So the utility of a member level distribution, you know, is limited, because I mean, how much good does it tell you to say like a 90% confidence interval is between $50 PMPM and $700 PMPM, right? I mean, that's limited, but we can use these distributions through a Monte Carlo simulation to look at group level distributions of risk. And it's those that I think are really critical, to be able to really compare groups distributions to each other and to quantify the group's percentiles based on each group's morbidity is really, I think, the power of this quantile regression, because it changes our whole perspective from comparing different groups' experience to each other within a block, kind of hoping that groups sort of follow the same distribution, so that we can say, well, if you have low claims within the block, then you're healthy. If you have high claims in the block, then you're sick. You know, instead of doing that, it's like allowing you to say, okay, relative to that group's experience, what does that look like in terms of the profile of possible outcomes that group could have in their claims distribution. So that's that. And then, of course, you can then further simulate from groups up to the block level to say, okay, here's my block level distribution of claims, and here's the variability of that block. Now, how does each group compare to that? This group is on the more variable side. This group is on the less variable side. You can stratify in terms of how certain you are of your predictions of each group within a block in order to help your underwriters understand the risk that each group is bringing to that block, and therefore how much you want to do in terms of discounting. So I've said a lot of words and not shown many numbers. So I want to do that now, just to kind of give you an illustration of what things look like at both the member and group level as a function of a quantile regression. So, you know, each member, unless they're very sick, is going to have a lot of percentiles very close to zero for a lot of percentiles, right? So like if you look at like member 0037, they don't really get any kind of significant risk until you get to like maybe the 85th percentile. And here, if you look at member 1706, well, they're much sicker, but even there, well, at the 80th percentile, they're at 3, but even at the median, they're only at 0.7. So like, but this is kind of what it looks like, right? We're coming up with this distribution for each member. So this distribution here for member 0691 is based on the demographics and conditions that member had in the base period. And here's what their distribution looks like. So I think these kinds of looking at this like line by line thing is very helpful to help you sort of understand what I call the 3 dimensions of risk that quantile regression really helps you out with. So, of course, you could take this whole distribution for number 1706, and you could just take the expected value from knowing all these percentiles, right? And that would tell you like a risk score, like an expected value of risk. So that's good to know, right? That's like something like our traditional estimates of risk, except you'd use it by estimating percentiles. And certainly that's a good measure of risk to know whether you have high expected costs. But you also know by looking at confidence intervals here, like say between the 25th percentile and the 75th percentile or something like that, you know like which members have high variance. So therefore you have uncertainty due to that wide range of possible costs. That's like the second dimension of risk. And then the third dimension of risk is these potentially catastrophic costs out here. You can see there's like a wide variability here, even among members that look not too different down below. They can be quite different up here. So if you look, for example, at member 2429 and member 6715, towards the median, they're the same. At the 65th percentile, they're the same. Even at the 75th percentile, they're close together. So a risk score would not really pick up a difference in risk between these guys. But if you were trying to laser them out for reinsurance or understand who is more risky for stop loss, you want to understand what's going on up here at the 99th percentile of risk, where now this guy is like practically triple or double, more than double the risk of member 2429. So there's a whole different kind of dimension of risk that's exposed by this quantile regression. But of course, as I was saying, these individual distributions are not really what we use in practice. You really want to aggregate those up to the group level. And so here you've got group 1198, everybody, and you kind of understand if their base PMPM is 380, you can say, well, that's really catastrophically high relative to the distribution they've got. So that could tell you something like, well, that means that either their distribution has changed because of some change in risk, or that you probably expect some kind of maybe a regression to the mean going down. The mean of this distribution is like 328. That's something like a risk score. Here's something like the increase from the 95th to the 50th percentile. And it's really very interesting, these group risks. If you start to aggregate different members together in different groups across your block, you can really see a very interesting distribution of risk among your groups. They really do look different, you know. Like, I mean, you really see something that you couldn't see before. It's pretty cool. So. So like here, for example, in this group, I'm just trying to say, so here I kind of added in these lower percentiles so that I could show that, like, here a 90% confidence interval for claims was like 291 up to 362 for the 5th percentile, the 95th percentile, and and that shape can help guide your underwriting, as I've discussed before. And I won't go through all these numbers, but here I'm saying you can use these quantile regression estimates to set like discounting rules, kind of based on where the experience falls. And this is like kind of a rough guidance that I've been sort of using so far, like where if their experience is less than the 5th percentile, you know, that's too dangerous, right? That means the distribution has changed and something has happened. But if they're in if their experience relative to their own group's percentile is something like between the 5th and 35th percentile, probably they'll regress to the mean upwards. If it's the 65th or 95th, they'll probably regress to the mean downwards, et cetera, et cetera. So it's really, you can come up with guidance like that, and you can kind of test different theories and see how it goes. So here's just a whole bunch of different examples of applications of this quantile regression that I've talked about. We've talked about a bunch of these. I'll just illustrate a few that I haven't mentioned before, like looking at provider practice patterns is a really good application of this, in the sense that, like, before you kind of measure a PMPM for a provider, a normalized PMPM relative to a group of similar PMPMs by using a risk score. But you know, you always know that there's some like margin just due to random variation, and this helps you to quantify that margin to say, okay, is it really true that like their practice patterns are outside the norm given the morbidity of their population, you know, or is it like within a confidence interval of some, you know, random variation? So you really only want to reward, you know, good behavior that's really like not due to random variation. You really don't want to penalize bad behavior that's not due to random variation. And this quantile regression quantifies that that variation and lets you make intelligent scientific sort of estimates of when that provider behavior is really something that you want to either give a bonus for or collect money for from the provider. So, and of course, just like with risk scores, you can really dig deep down and see which conditions are driving that aberrant experience. You know, looking at just the different slopes of the different conditions, right, of those risk scores itself will tell you quite a lot. So I'd like to just motivate the use of this quantile regression and this idea of like using regression to the mean, just in terms of like using prior claims and relative claims relative to where a group is in terms of its block is really a dangerous thing to do. There's so much just random variation in terms of like where claims end up in which part of their distribution in year 2 versus year 1. Very few groups are stable enough from one year to the next to really just use prior claims, you know, itself as a sufficient sort of estimator of that. So in this slide, I'm kind of talking about like linear regression versus quantum. You can see this is my favorite picture from the fact that I have it again here. But here we're just looking at these different impacts of these different percentiles relative to what a risk score would tell you. This is like the slope of this line is like the risk score. The slopes of these lines are like the quantile regression. So I just want to mention that, here I've talked about 2 new estimates that you can get from quantile regression. And this opens up a new world of estimators. that we've got. So one of these is like a prospective quantile regression, just like a prospective risk score, where you could say, well, instead of using the mean, which is like your risk score, you could use some kind of weighted average of percentiles. And for the distributions of claims that that you get from health insurance, that weighted average of percentiles actually is a pretty good estimator. It's biased, of course. Only the sample average is an unbiased estimator, but it has much lower variance to use that. So you've got a prospective one. We've talked about regression to the mean from a retrospective quantile regression. So now we're talking about four estimates already, right? Like, so prior claims trended, what your traditional symmetry risk score would tell you, what a retrospective risk score would tell you, and what a prospective risk score would tell you. So now all of a sudden you said it's hard enough to learn how to correctly blend two estimates together, and now all of a sudden now we've got four estimates we have to find a way to blend in an optimal way, and that's a different talk. But you can see how that like opens up a lot of other interesting statistical problems that we really haven't even scratched the surface of, right? Like, what's the right weight to give to those estimators? How correlated are they with each other? And how do you avoid like double counting when you're looking at like prospective rates? So let me talk a little bit more about stop loss real quick. So for both individual stop loss and aggregate stop loss, you can sort of quantify at the different percentiles basically what the whole distribution of risk looks like, and therefore where you want to set your premium in order to control your probability of loss, right? I mean, you can't ever, we've talked about how like traditional risk scores are not really effective for estimating what the risk is for different kinds of stop loss premiums, but we haven't really quantified much like how you could actually use this quantile regression to understand how to set the premiums for both your individual stop loss and your aggregate stop loss. But there's really two sort of things to understand. First of all is how do you set the relative risk for your group at the 99th percentile or 99.5th percentile, or way up there in the tail, right? Which is one critical problem. But then also, what's your correlation look like between your individual stop loss and your aggregate stop loss? There's a covariance between those two, between the incidence of claims in the ISL and the incidence of claims in ASL that you need to recognize. And if you don't recognize, you're going to price wrong. So this quantile regression will allow you to come up with that bivariate distribution, which will help you to price your stop loss risks better. So let me just spend just a few minutes with a little bit of a statistical nerdishness. We've been talking a lot about how like least squares is a matrix equation, and this is a way harder problem to solve. So what really are we trying to solve when we're estimating these quantiles and these conditional quantiles? So there's really an interesting parallel between our risk score estimates, our least squares estimates, which is doing something like this, right? It's minimizing the squared difference between here this beta represents all the different coefficients you have, right? Whether it be age, gender, your conditions, et cetera, et cetera. So this is a nice function, right? This is how you get your risk scores. This is how you get the contribution to the mean from each covariate, and it's a nice function, right? The reason why this got so popular in the first place is because you can differentiate a squared, x squared, right? And you can easily minimize this function. It's a nice parabola with a unique minimum, et cetera, et cetera. So the reason why this quantile regression hasn't been used and it's so much harder is that instead of minimizing this squared function, we're minimizing this weighted average of underestimation and overestimation. So here we're looking at like overestimation, and we're saying, so for like say the 25th percentile, that means this is 0.75. So we're heavily penalizing overestimation. We're pushing down the estimate to get to the 25th percentile. And we're also penalizing underestimation with a 0.25, so a 0.75 and a 0.25, right? And so, and each of these is absolute values. Of course, absolute value is not a good function, and it's hard to do, right? So it's interesting to note that, like, here we're minimizing this, and when Q is 0.5, when we're trying to estimate the median, we wind up just getting the sum of absolute values, which we're trying to minimize. So that's like a special case, right? And so this was really, really hard up until they realized that you can frame this as a linear programming problem, which is nice in the sense that there are many tools to solve linear programming problems, but it's still exponentially harder as you get a lot of data. So, and that's like meaning like greater than 100,000 points or so. It's just hard to search around and find the right coefficients that minimize that. So, and the reason is because, you know, even in 2 dimensions, it's easy to get stuck in a local maximum, right, relative to looking for, like, say, the global maximum. So you really have to find a smart way to search around and find the right coefficients that will help you, you know, to find the right numbers that minimize those that weighted average of penalized over and under estimation. So. So that's pretty much, you know, kind of good for an introduction. We're looking here at, you know, like, it's really interesting how, like, some coefficients will be significant at lower percentiles, but then not be significant at higher percentiles, or vice versa. So it's really interesting to look at things kind of one coefficient at a time, but then also to kind of aggregate up to the individual and group level. And so, you know, you just have like a whole new set of tools in your toolbox. So let me just kind of go back to the sort of motivating problem in the first place, right? Which is that we want to build effective confidence intervals because we want to understand how to understand experience in terms of group morbidity. So it's all about expanding our understanding of group morbidity to go from just a univariate sort of expected value perspective towards like a multidimensional confidence interval type perspective. And that's what quantile regression is all about. And so thank you for your time and attention to this somewhat technical topic, but I do think it's very important, and it really represents a new frontier for us as health actuaries. So I'd be happy to take any questions that anybody has.
Thank you, Jason. That was wonderful. I think we enjoyed hearing about the introduction to both the technique, the methodology of quantile regression, as well as hearing about the application of the technique. So like Jason said, now anybody from the audience is welcome to just unmute yourself and ask any questions. I'll leave some time for that. Okay, I'm not hearing anything coming so far. We'll come back to the audience, but I do have a question that came in previously here. So the question is, how does quantile regression compare to more modern machine learning estimates like gradient boosting or neural networks, etc.?
Yeah, that's a good question. So quantile regression is like an expansion of traditional linear regression. So it instead of like trying to predict the expected value by minimizing sum of squared differences, it's minimizing this weighted average of over and under estimation. So it's like a minimization type problem. So a lot of modern day data mining techniques do a similar type thing. So in fact, if you try to they take a loss function and they try to minimize that loss function in order to come up with, say, the proper gradient boosting thing. So you can get what's called like quantile estimates out of these machine learning techniques, but this quantile regression in the sort of in the context in which I presented it here is more similar to regression in the sense that we get we specify what the predictors are, and we get the relative impacts of those predictors at each level. So you can kind of trace for each coefficient what each of its impacts are. The modern machine learning techniques don't really allow you that kind of flexibility in terms of each predictor. You can kind of back into estimates of variable importance, but you can't really get the same kind of richness of description of data that you get from quantile regression.
Great, thank you. I have another question here. How much data do you really need to produce good quantile regression estimates of the health claims distribution? I guess more question on practicality.
Yeah, that's another good question. You need a huge amount of data to do this really effectively. If you think about so if you think about a regular linear regression, a regular risk score, right? Usually like say 200 different like medical condition categories or pharmacy condition categories that you can use, and to get stable estimates using your normal least squares regression, you can get away with maybe 500,000 records or people or something like that. But here we're estimating so instead of just a single value for each covariate, we're estimating the whole distribution for each covariate, right? So there's many more parameters. So even if you only did one estimate for each percentile, that's 100 percentiles times 200 estimators. So now we've gone from 200 to 20,000 parameters. So you really need millions of data points to get good stable estimates of the contribution of each variable.
Makes sense. Makes sense that it requires heavy amount of data. Now I'll just turn it back to the audience online here if anybody would like to ask a question.
Hi, this is Audrey Jason. Good talk.
Thanks.
But how much variation in underlying claim cost would you need for this model to produce, say, significant differences? So I can see uses for medical, pharmacy, but for something like dental, would this model even make sense?
That's a good question. Yeah. I guess it's all about, I mean, of course, since it's just a formula, it'll give you, you'll get different distributions, right? Even when you have very low limits, like in a dental type situation. So the question is do small differences make enough of a difference in a practical matter, right, to matter? So I guess the question would be how close are the prices, when you're in a competitive bidding situation, right? How close are the prices to each other, and how important is it to get that kind of level of precision? So that's a great question, right? I mean, for dental, it's kind of exciting, right? Because there's at least as many predictors, right? If you think about all the different dental procedure codes and how many teeth there are and stuff, there's at least as much going on with dental in terms of utilization, right? Variances but there's just not as much difference in the actual price, and in terms of how much is paid. So I think it's a good, it would be a good exercise, and how much time you spend on that exercise would be determined by how much that accuracy would really help you.
Thank you for that question. If anybody has any other questions, feel free to go ahead.
Hey, Jason, thanks again for doing the talk. We got a question in the ACHS inbox. Earlier on, you mentioned how this quantile regression has sort of been unlocked with modern computing power, whereas linear regression needed to be relied on more in the past. Is there anything that you're aware of that we may sort of be on the cusp of in terms of more advanced regression that we can't necessarily do now, but in the future it'd be beneficial?
Well, that's a good question. I mean, one thing that I think is a very good like practice is like trying to understand like which variables are really the most important to predict future health claims. So like, let's say in practice, there's like 300 different categories, or maybe throw in pharmacy, maybe there's like 400 different categories that you care about. I'd really like to know which subset of those predictors is really the best, right? That's really critical. Which of these are just adding noise, and which of them are, and right now we really don't have the ability other than by using our judgment to know that. But like, you know, if you think of like a stepwise type regression or a backwards where you're doing like variable selection, but that requires like tons of comparisons, you can't really do that kind of regularized regression. At least I've not been able to on the gamut of variables that we have to choose from. So like, you know, so like even to do the most effective risk score or the most effective quantile regression, basically, you know, I just throw every variable at it, right? So, but like in some sense, you know, I worry about like spurious correlations, and it would be nice to know like what subset of them is the best. So that I think is like the next frontier. With like, you know, some supercomputer, you know, I could then, you know, you wouldn't even need to worry about it. Just put it in there and let it rip.
On that topic, why would you not do something like cross-validation, like to say like, hey, if you remove this predictive variable, then how do I do,
Right.
and different splits. So like, why would, if you're concerned that a variable isn't working, does that technique not work?
Well,
for you?
You could do it like, but like how many, like, so there's so many, like it's like like say 400 is our number, right? So it's like 400 choose one comparisons plus 400 choose two to get the two-way interactions plus 400 choose three plus, you know what I mean? It's just some like humongously enormous number of comparisons.
Then can't you do something like a elastic or like the what is it, elastic net regression, like where they have lambdas that penalize you
Yes.
based on coefficient values? Or is that not effective for quantile regression? Or is that too complex?
Wow, that's a good question.
I'm not sure the state of the software.
Yeah, well, let's say you programmed it yourself, right? I mean, you certainly can. So, like, but suppose you're saying, why not program it with a penalty term to penalize overcomplicated models? Why not? Yeah, no, I mean, that doesn't exist today, but I don't know. Yeah, that would be great to find out. Well, but you'd have to program it. Yeah. So I mean, that's
Okay.
So there's only a practical, I guess, limitation, and that would be very nice because they say that those like elastic net, or actually, what is it, the one with the absolute values? What's it?
Lasso and Rig.
Lasso. Thank you. Right. You know how that one like zeroes out the variables that are not important, right? So it'd be cool to kind of play with that parameter and see if it worked.
Great, thank you. Anybody else from the audience?
Great. Well, thanks for your attention, and feel free to contact me anytime with any questions, or if you want to talk further.
Thank you. Thank you very much.
So.
Thank you so much, Jason. Really appreciate it. To our audience, please come back for tomorrow's final session for the summer CPD week. We'll have David Lipke from MassMutual talking to the impact from the private equities on the insurance industry. I'm sure it'll be a very interesting talk. So thank you very much. Hopefully we'll see you tomorrow.
Thanks, Jason.